Okay, so today's topic is larger infinities, and it's not necessarily restrictedly larger infinities. It's just the idea that not all infinities are the same. Now, this is a very confusing topic to someone who doesn't have necessarily a math background, because infinity being the largest number possible, or a theoretical number that you cannot reach if you started counting upwards, but it is the limit. Um, so infinity is such a large number that if you add one to it, it's still infinity. But it's a confusing concept because it's theoretical and it is the limit that you approach. Um, it's not so cut and dry. Things are very abstract. But what I want to explain is that so there's some paradoxes that come with the number infinity. So we can't say in a normal situation, say we had the number 6. If we divided it by itself, we would get 1. And if we took 6 and multiplied it by 0, we would get 0. But simple operations like this don't really work for infinity because there's information we don't have. We don't necessarily know that one infinity is not greater than the other unless we have some extra information. So, what can happen is we have to look at the limits of things. So, let's take two things that, as x approaches infinity, also approach infinity. So, we can take function 1 of x to equal e to the x. So that's just an exponential, e being the Euler number, but this isn't specifically important that it's e. It could be 2 if you wanted it to be. I'm just doing this because it's a pretty common function in mathematics. And we'll say function 2 is going to be x squared. So we have two functions. Both of them, as we put bigger and bigger numbers in here, get very big. And they become large faster than x itself becomes large. But there's some interesting things we can think about with this. So if we are thinking about the equation, so we're going to say the limit as x approaches infinity of a combination of these equations. So if we take e to the x over x squared, well, if we look at the graphs of these two functions, x squared goes up and it gets fairly vertical pretty fast, but it does continue to approach infinity. So this number is getting very large as x gets large in general. Now, e to the x is somewhat of a different case. It approaches, it becomes large extremely fast. And so this isn't a perfect picture. I'm just trying to give you an idea. But if you imagine that, let's say 2. If we had 2 to a power, then we know that it's numbers that we normally use. It's so 2, 4, 8, 16, 32, 64, 128, 256. It becomes large pretty fast, and there's an interesting puzzle that I think I can't remember the exact context of it, but essentially someone was saying that they wanted someone to take a chessboard and put a grain of rice on the top left corner and then move to the one next to it and put twice that and continue doubling all the way down the chessboard. And by the end of it, you just had some crazy amount because exponential functions increase very fast. So what I'm getting at is that e will approach a significantly larger number than x if we put x squared than if we put a large number in here for x. So the limit of e to the x over x squared as x approaches infinity is actually infinity because there is a very large number being divided by a less large number. So we still have a large number. It's greater than 1. It's greater than 0. It's greater than 1. So it's not a regular fraction. It's an improper fraction, if you want to say that. But if we flip this, the limit as x approaches infinity of x squared over e to the x, then we find that this is equal to 0 because there is a very large number dividing a significantly smaller number. You can think of it as 1 million under, let's say, 100,000. Well, okay, let's just plug in some numbers for context here. So if we wanted to put in, let's make this easy on me and make this 2. And so if we're plugging in numbers here, let's pick a number that just off the top of my head, 100. 100. So if we plug 100 into our first function here, we're going to get, I'm going to do the math on this just to make sure I'm correct. I always have my phone not in the rotationally locked, so then I have to unrotation lock it for the calculator, and it's somewhat annoying. And it doesn't seem to be working with me, so hold on. Okay, so 2 to the 100 is a very large number. That is on the magnitude of 10 to the 30th. And if we take 100 squared, then I think you know where this is going. We get 10,000. So if we are just rounding here, then we have 10 to the what is that, the 4th, because 100 squared is 10 to the 2 to the 2, and then 10 to the 30th, and you can see how this is less than 1 by a lot. But then if we flip this, then you can see that it is still significantly greater than 1. It is a huge number. So this is the idea that not all infinities are the same. Now, this can become confusing when we step out of multiplication and into the realm of addition or subtraction, per se. There's actually a famous proof that if you have a properly set up infinite series, which means it's like a pattern of numbers, I think if you say 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on, you can rearrange this so that it equals to whatever number you want. So what this basically means is, since we have 2 series, so we can say the odd indexes here, so 1 over 1/3 plus 1/5, and then we also have the even indexes here, minus 1/2 minus 1/4 minus 1/6 dot 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 dot. Both of these series that we've split up here, both of these series that we split up here approach their respective infinities. I'm not going to draw a line between them. So this series approaches positive infinity, and this series approaches negative infinity, because everything is negative. So what's happening is here is we're subtracting this series from this series, but the order that we do this in actually can change the outcome of the convergence. So if we what we can do is we can make this idea of infinity minus infinity equal to anything, because infinity plus 4 is still equal to infinity. So we could technically say that infinity minus infinity is equal to 4. Um, Now, it's somewhat of a paradoxical idea, but it is something that is very well thought out, and I believe I think it was Raman. So, if you've ever heard of the Riemann zeta function or uh, Ramann's last theorem, he's a very prominent name in mathematics, but he was the guy that actually thought about this and put it down on paper. So I think that I have explained what I came out to explain. Sorry if I'm fumbling over my words a little bit. I was working on the game for uh, the entirety of today, pretty much from about noon until now, with little breaks for food. So I'm going to be moving on to the final section, which is the random drawing.